And we are down to our last, but not least, presentation. I was able to arm twist Don Henninger into coming in and giving us a talk. Don knows more about the engineering and construction of habitats than anybody I know. And so I had to come in here and get him to brief us a little bit. So, Don, if I may.
Thanks, Mark. I'm going to describe an approach to investigating these things, which goes well beyond investigating the microbial aspects of human spaceflight. I'd like to make one point, however, first, and that is that these larger systems where we intend to recycle things, keep things in the systems, are destined for their best application is the planetary surface, all right? We won't have vehicles that are ever going to be big enough to do anything at any reasonable scale. So that means we're going to be doing those things on the planetary surface where we have the ability to accumulate infrastructure with both manned and unmanned missions to get that infrastructure there. Leverage resources we have available to us, particularly on the moon. In terms of the moon and Mars, we're going to be going to the moon first, okay? We knew well before Apollo over our next destination should be going back to the moon to prepare to learn how to go to Mars. We knew Mars was just too far away, way too ambitious, too many risks that were not defined, that we didn't know how to deal with. Well, we'll go back to the moon and we'll investigate all those things and create an infrastructure there that we can do either permanent or semi-permanent occupation. The other thing was that the moon represents a resource base in the context of perhaps going to Mars. As you would expect, getting on and off the moon is a heck of a lot easier than getting on and off the Earth, right? So if we go to the moon, build infrastructure, we can use resources from the moon, take them to space to outfit a Mars vehicle to go to Mars, and export things to go to Mars as well, other resources in unmanned missions, and leave from space. That's sort of the notion with the Gateway vehicle that you've heard something about lately, and I have one slide that I'll show you what that means exactly. And Gateway is something that's not a new concept either, okay? The next step we talked about in terms of going back to the moon was to establish a capability in space at one of the libration points, one of the Lagrangian points. Why? It's easy to stay there. Why? Because we don't need to come back to Earth every time to do everything. And we knew on a vehicle to go to Mars, for example, we had estimated years ago, I don't know what the recent estimate is, that it would be as big as the space station because of all the mass you would need, all the supplies you would need to go there and to come back for a 3-year mission, 1,000-day class missions. So did you want to launch all of that? Where were you going to put it together? Low Earth orbit? Not a good idea. It takes a lot of energy to stay in low Earth orbit. You could do it at a Lagrangian point, which again goes back to the Gateway notion. You accumulate infrastructure there. You do vehicle assembly there. Furthermore, if a Mars returning vehicle comes back, where do you want to take it? Not the low Earth orbit, not even to the Earth's surface. So you take it to a system orbiting the moon in some fashion, and you refurb that vehicle, use it again. And that's the notion again with the Orion vehicle. That's the transportation. Orion is the only vehicle, by the way, that can come back from deep space. No other vehicle that exists or be on the books even has the ability to come back from space because you're coming back at so much higher velocities for a direct re-entry from deep space. We can come back from low Earth orbit, but we're coming back at about, I guess, less than half the velocity. So Orion is actually something we desperately need to come back from places like Gateway. And that's the whole notion. And these are all old concepts. We had plans on the books that I know of since the early 80s to do that. We had workshops, we had symposia, we invited all the best world's experts in to advise us how should we proceed. And guess what happened? Somebody threw a huge dose of politics into the equation multiple times. And Brad can tell you, we had a fairly good notion of where we wanted to go and how to get there for the most part. And if they just would have left us alone, give us a nominal budget, we would probably be there by now. Anyway, let's get started on some of these slides here. A little bit of philosophizing. I've been with NASA a little over, right at 42 years now, and I had another 10 years as a contractor prior to that. So I have the corporate memory on some of these things, as does Brad. Okay, how do we proceed here? There we go. Question: how do we assess the full impacts of a dynamic microbial community? And it's dynamic whether you want it to be or not, no matter what kind of exercise or control you desire to exercise over it. And the time function on this is quite different and has impacts on how you look at that. Transit vehicles are days to months. Now, yeah, the station is in Earth orbit. It's been in Earth orbit for a long time. Crew stay there for 6 months. But you got to remember, we're only about 90 minutes away from an abort. We go to the moon, we're like minimum 4 days away from an abort. We go to Mars, you're about 400 days away from an abort. You got to go all the way out around orbit for a while and come back. So those abort scenarios dictate you do business differently than we do on station, for example. So the planetary surface infrastructure was going to go from months to years to permanent, most likely. How do we get a handle on what we're doing? Now, you guys are doing a whole lot of work with station, and I understand why we're doing that. But what concerns me more than anything is that we're not doing an equivalent body of work that we're doing on station on the ground. And by equivalent, I mean a single vehicle, a single huge system, a very dynamic system. And in your case, from a microbial standpoint, that is a feature of what we're doing. You do not have access to a sufficiently high fidelity ground test equivalent to the station. Okay? There's no closed environment ground test capability capable of housing humans for extended periods of time. And I'm talking about months and months at a time. Okay, somebody mentioned earlier the Russian facility where they did that 500-day test. That was open atmosphere. Okay, they didn't have elevated CO2. They were exchanging air with the building air. HERA does not have a closed atmosphere. They're oriented towards psychological and circadian rhythm sorts of analyses, and I understand all that, and that makes sense. But there's no equivalent where we have a closed environment, including the humans, for extended periods of time. Now, what I had wanted to do back in, I started it, I think Brad remembers back then, in the 90s, early 90s, was to start developing a test bed where we could do that. And to do that in such a way that it was very high fidelity, we could include humans, and we'd carry out a mission as though we were in space, we were just on the ground. So we kind of used the monogram, fly the mission on the ground. In other words, make it look as though we're a mission. In fact, define a campaign of missions that got progressively longer, progressively more complex, and entertain not only the research that was primary for those missions, but all the other elements that would be required. And we were oriented primarily at that time from a standpoint of life support systems, because we knew we had to do a lot of recycling. We didn't have the place to do a high fidelity testing for that. So that's what we need. And you can evolve such a facility. You don't have to build it all at once, right? As I said, you can develop a campaign of missions that will drive a certain ground test bed capability, and that's kind of the way it would go. But some of the key attributes, it has to be sealed atmospherically. Lots of things will happen if you're exchanging air with Earth air. And it has to include humans. That's the whole point, right? So, and there's you can list a whole bunch of attributes. And the other important thing is that this facility, which is unlike the station, we can instrument the heck out of that thing, right? And we can get samples out of that thing in a hurry. You're very limited on the samples you can get back from space station, and you sure can't put your laboratory on the space station. Here we can put the laboratory in the next building, right? We can even use things like direct sampling, direct lines from the facility to the lab. So what we're trying to get to is a sustainable human presence off Earth. And I'm not sure what that means necessarily. We always talked about self-sufficiency, independence from Earth resupply. If you look at any of these missions, the major risk, the weakest link in the element in that mission is resupply from Earth. Because that can get disrupted very easily and for quite a long period of time. Now, what we're trying to do in terms of keeping humans alive on these very long missions is to duplicate the functions of the Earth, right? The Earth has these huge buffers, land masses, the oceans, atmospheres. And the question becomes one of how small can these buffers be in reality, and still be able to maintain something that I've kind of dubbed a dynamic equilibrium. And by that I mean you're measuring hundreds and hundreds of variables on this human system, if you will, and you want to keep them all within some reasonable control. And we don't know what that is, but over a period of time, if you do that, can you achieve some system stability over very long periods of time? And I don't know whether you can or you can't, or I don't know how much control you'll need to exercise in order to do that. But the notion is that we don't have surprises. And I don't know any other way to do that other than to do it on the ground. And oh, by the way, somebody earlier said that they thought that 1/6 G of the moon was more like microgravity of station than it is to 1 G. I believe just the opposite. That the 1/6 G of the moon, particularly the 3/8 G of Mars, is more like 1 G than micro G is to anything else. Micro G is just a blasted, strange environment, okay? And it drives us nuts all the time trying to, how do we separate out the 0 G effect from everything else that's going on? And it's really hard. But anyway, I like the moon's gravity. I don't know whether it's good. It's going to drive us crazy in terms of unsaturated flow through a porous media, for example, the soils that Penny talked about. Man, that's from simple soil physics we have to start on. Then we talked about starting on that very thing in the late 80s. And then politics stepped in. We reorganized, the funding went to hell, and we didn't get to sustain that effort. Starting to come back a little bit. We actually have done some of this kind of testing I'm talking about back in the 90s, believe it or not. I think if you were here on Wednesday, I mentioned that the longest test that the United States has ever done or sponsored, NASA I'm talking about, was 91 days. And that was in 1997. Quite a while ago, huh? But the first test we did was for 15 days with one person in 95. He was in a chamber adjacent to this wheat growing chamber here, where we had 12 square meters of wheat growing. And all of his oxygen came from the wheat, and all of his carbon dioxide was consumed by that crop of wheat. I don't know if anybody knows Nigel Packham now. He's our associate director or director of safety and mission assurance here at the center. So he had enough gumption to go in this thing for 15 days. We razzed him for weeks and weeks afterward, of course. But it worked fine. There were no surprises. Now we did it at the maximum crop canopies structure, because that's where we could get one full equivalent, because it takes about 12 square meters of plant growing area for one person. So if we're taking a crew of 4, we'd need roughly 40, 48, 50 square meters of growing area. You can't do that in a station, for example. And then we do 3 more tests, a 30-day test, a 60-day test, and then the 91-day test I spoke about. We learned some things that were quite unusual. One of those tests, we had started to see formaldehyde levels increasing. And where in the blazes is this formaldehyde coming from? So we did some background work, looked at everything that could possibly be contributing to the formaldehyde, one of which was, photographic film, clothing, things like that. So we had them pass out all of those things out through the equipment pass-through, which is where we could minimize atmosphere exchange. And it still kept on going. We had a trace gas contaminant control system, but it was only keeping pace with whatever was creating this. So we got to the point where we were above NASA limits on formaldehyde for spaceflight, but we were below OSHA limits. So they allowed us to stay and test and monitor it several times a day, and I had to report out the formaldehyde level every day to senior management. It's the only way we could stay and test. Turns out when we were done, we did testing of other materials that were in that chamber at the time. And what we had done was gone in with this foam egg crate material to attenuate sound. And that was the source of the formaldehyde. So before the next test, we just ripped all that stuff out, of course. We outsmarted ourselves. I think it was either the 30 or the 60-day test. It might have been the 60-day test. We also, at the time, were using iodine as the residual biocide in the potable water. And iodine had been used since day one in spaceflight, up to that point. And during the test, the surgeons, the medical side of the house started seeing some unusual thyroid function data. So they went back and reviewed all the flight data. And they saw things in there which didn't make them very happy. They couldn't draw any conclusive conclusions from the data, but they ordered us to remove the iodine before any more crew consumed that water. Not only that, they ordered the space shuttle program, which was flying at that time, for the very next mission to do the same thing. So you learn a lot about these things in these tests that impact the flight programs. What else was there, Mark? There was one more thing, wasn't there? I don't remember. Anyway, Mark and Dwayne Pearson, his predecessor, did a lot of micro work during this test as well. During the 91-day test, which was primarily an ECLIS test, a life support test, we had on the order of between 25 and 30 co-investigators that came in on a non-interference basis to do work for which this environment that we created was very valuable. And that was the last test that the U.S. has ever done. Question, is the 91-day test long enough to prepare for a 1,000-day mission where you have a little difficulty getting back if you got a problem? I wouldn't go. I don't know about you guys, but I wouldn't go. So probably not. The idea is to manage the risk. Well, there's always going to be risks. But I'll tell you, it's really hard to manage a risk you don't know about, right? If you can't identify the risk, you can't do a dang thing about it. So that's the idea. First, you have to identify them before even managing them becomes an option. And how do you do that in such a complex system? And boy, this is complex. The other advantage you have in a ground test system like this, you can instrument daylights out of it, right? You can pull samples at a high frequency. You can change all those things as you're going through the test if you see it's not necessary. You have access to very robust, capable analytical laboratories. Oh, by the way, did you all think that when you went back to the moon, one of the things you're going to have to take with you is an analytical laboratory? Okay? So you better figure out what kind of instrumentation you need and how to make it the size of a bread box. With no consumables. It stays in cal for months to years at a time, and when you have to cal it, it doesn't require consumables. You better get started working on that one. This is the other interesting one I was going to point out, Mark, was, I don't know if you remember this one or not, but this was the trace gas contaminant plot for selected trace gases. And on here we had acetaldehyde, ethanol, isopropanol, and methyl cyclosiloxanes. Anybody know why that's important? Because we have run into this problem on station. And in 2010, and actually we're still dealing with it to tell you the truth, where we had these complex siloxanes. And where they come from is they're in shampoos, toothpaste, wipes, which we use all over the place on station. That's the source of most of these complex siloxanes. They're ubiquitous on Earth. On Earth, though, they're dealt with by the soil medium, okay? The silicate clays take care of all that for us. Now, why was it a problem on station? They're not, you see, we got pretty close here to, where's the pointer on this? I don't know, with it. We got close to the SMAC limits for those, which was 12 milligrams per cubic meter. We were getting close there, but the test was done. We didn't know where they were coming from. We didn't necessarily know what the impact was. But we obviously knew we were going to have to remove them at some point in time, but we didn't worry about it too much because the test was over. Follow-on test wasn't planned, wasn't funded. So, however, station had those on station. Now, what happened on station? They were in the atmosphere because they're volatile. Okay, and we have condensing heat exchangers on the station, right? Control temperature and humidity. We coat those heat exchangers with a silicate coating. Why? So that they're hydrophobic. We want to pull water out of that. We don't want just to condense it and shoot it right through the other end back into the atmosphere. So we use that hydrophilic coating, to wick that water away. Well, guess what? It acted as a catalyst on those complex siloxanes and turned them into a simpler siloxane, namely this DMSD, dimethylsilane diol, which, hey, guess what? It's now soluble in water. Well, guess what again? The water system wasn't designed to remove it. So guess what? It went through. Now guess what? We're measuring what to determine potability of water? Total organic carbon. Whoa, total organic carbon is going up. What now? Well, if you get to a certain point, you got to either recycle the water or stop drinking it. So what we did was we changed out these big multi-filters that are part of the water system. They're big. They're about this tall, about 6 to 8 inches in diameter. You take 2 of them, they weigh about 80 kilograms a piece. And they're not cheap. We replaced them. Okay. That took the level of organic carbon down. About another year later, it started going up again. And these multi-filter beds are designed to last several years at a time, based on ground testing. So why aren't they lasting? Because they weren't designed to remove DMSD. So what do you do now? Well, we're still replacing the multi-filters, but we're also doing other things. Giving the crew options to select shampoos, toothpaste, deodorant, and wipes that don't have siloxanes in them. So that helps. We're designing a better catalytic oxidizer for the air that will remove those complex siloxanes from the air so it never gets in the water. And lastly, we're looking at different coatings for our heat exchangers so we don't have that reactivity problem. Okay, so that was a case where, hey, we were just about on the cusp of figuring out a problem that we might have in the future. We didn't get to investigate it anymore, and it did turn into a problem. Still is, actually. We were actually working on another facility much larger than the one, we have this thing here. Here is this test facility that we did use to, this one over here, how do you turn the stupid pointer on here? There it is. That was the chamber we used to run these 30, 60, 90-day tests, okay? It is about 20 feet in diameter, 3 stories tall. Pretty nice chamber. Airtight, of course. We outfitted it with all the water recycling and air recycling systems that we had at the time, the best we had. And it ran for 91 days. So when, I think, while the crew was in there, they drank the same water 6 times. Okay? And by the way, that was the first time anybody, anywhere on Earth, was allowed to drink recycled water, part of which came from urine. Okay? We had to get special permission for all that. But it worked. Now, the idea here, this chamber still wasn't big enough because obviously we eventually wanted to grow crops to provide food for the crew and so on. So we started working on another facility, much larger. So we started building these chambers here, which were airtight. They were 37 feet in length, 15 feet in diameter. We sized them stupidly to fit in the cargo bay of the shuttle. It was arbitrary because we didn't know how big they could be. We didn't know what the future launch vehicles were going to be able to take. But it was all a ground test bed, okay? So they were all only designed for ambient pressure. And that's a sidebar I'll tell you about in a little bit, which might affect your work about pressure. So we had 4 of these big chambers and the interconnecting tunnel already built over in building 29, if anybody knows where 29 is. And guess what? We got reorganized. Politics strikes again. Reorganized. The Office of Life and Microgravity Sciences went away. The emphasis was space station, so it was all hands on deck to build station. Guess what? That meant all the money went to station as well. This money went away. And Orion started up. That also claimed a lot of resources. And at one point they said, hey, guess what? For Orion, we need an avionics integration laboratory. We had one for shuttle. It takes pretty much a whole building. And they said, where are we going to put it at JSC? Let's go look to see where a building exists that nobody is using. They asked about this building. I said, I'm using it. Well, who the hell are you? Where's your fund source? And it was but, and it didn't matter. So guess what? Those things were cut up for scrap metal. And the building refurbed. And to add insult to injury, they never built the avionics integration lab. This was the interconnecting tunnel where we were running all the utilities. we had one of these designed to be, and we had pretty much the design complete. In fact, we'd gone through PDR, where we had a human habitation module, another module for the physical chemical systems, 2 modules to grow plants to the tune of 150 square meters total. And I don't know, we had another chamber. We were going to put an airlock on the end of it so that we could go out into the building and do a real EVA with weight relief systems so that we didn't contaminate the air and go out in real suits. But anyway, that was sort of the plan. Here's where the modules were: life support, biomass, 2 of them, utilities distribution. I had a C of F where we had to modify the chiller plant, the center chiller plant, to bring big cooling lines into the building. Because if we lost power, we needed auxiliary cooling because we knew we were using quite a bit of power. Anyway, we thought about this earlier. WinterBased Agriculture. I give it $100 to anybody who ever read that book. It was based on a workshop. And this was a workshop until 1987. The book was published in 1989. And at that time, we were saying, we're going back to the moon. We want to grow plants at a reasonably large scale. Can we use the lunar regolith as a substrate for growing these plants? And if so, what would we need to do to it to make it a viable substrate? So I invited experts from all over the world to come in and have a workshop, a 3-day workshop. Emphasis on work, which is what I told them on the first day. And they were expected to contribute each a chapter, a significant chapter, on both research, the research record to date, and what the recommendation was for the future. So that was what's in this book. Now this is the last slide, and I'll get off the stage. I wanted to show you this because this is the near-term future, if you will, unless politics strikes again, which it could. This is Gateway. See, this is the Orion module, the Orion vehicle, coming to dock with the Gateway, and it will dock right there. This is Gateway, this module, and this is the power and propulsion element here, I think. This, believe it or not, is the lunar vehicle. This at the bottom is a tug, a propulsion system which will take this and this to the lunar surface. We'll drop that off before we get there when we get into low lunar orbit. This and this will land as a unit on the lunar surface, stay there for 6.5 days, and then this will come back up to Gateway again. And that will be a lunar surface mission. The reason it's 6.5 days, it's a half day down, half day up, and 6.5 on the surface, is that the orbit of the Gateway, which is in a near rectilinear halo orbit, which means it's orbiting the moon and at a libration point. Is it L1 or L2, you remember? I don't remember. I think it's L1. Anyway, it's orbiting that, and that's a fairly stable orbit. It's relatively easy to stay there with relatively small amounts of propulsion. And so it comes around every 7.5 days. So you get on the moon, you got to stay there and you either come back within about 2 hours, you have an abort situation, or stay there for 6.5. And it's a pretty Spartan vehicle. Originally baseline to get 4 people down and up, 2024 limitations and our ability to meet the mass limitations for that thing. We backed off now to 2 people on the surface for 24 and 25. But believe it or not, there are no technological limitations to doing this. We can do that. It takes money, it takes leadership, and it takes work. But we can do it. We already have probably 1,000 or more people working on it seriously. We're going to put out a procurement here in about a month or 2. I think July it's supposed to come out, for commercial bidders to bid on building a version of this, and that, all 3 elements. And the plan is we'll make 3 awards. One of the first 2 will go to the moon in 2024, the other will go in 2025, and the 3rd vendor will drop at some point before the missions begin. And that's pretty ambitious. So we're putting out a broad area announcement, which means that the proposers have a lot of latitude in trying to subscribe to the limitations we put on the procurement, which will have something akin to requirements. And we won't get too specific, but specific enough so they don't take us down some rabbit trail. So that's the plan for going to the moon. And then when they get back to Gateway, Orion is docked, remember, they get back in the Orion vehicle and come back home. They have this service vehicle on the Orion that drops off on the way back, and then they just come in with this, with this capsule thing. Questions?